First, I would like to thank the Harvard Foundation as well as Professor Nolan for inviting me here and giving me the opportunities to perhaps clarify some of the stuff we've been talking about. It is actually this year will be 30 years that I've been working with carotenoids. And I cannot give my presentation without adding a little flavor to the autobiography of lutein and zeaxanthin. Because when I first began my work in 1983, I was hired to look at the fruits and vegetables for the levels of beta-carotene because National Cancer Institute was interested to know the amount of vitamin A activity in these fruits and vegetables. I think it was about a couple of months into my research when I discovered that fruits and vegetables are much more complex than actually National Cancer Institute is thinking. I basically paid a lot of attention to oxygenated carotenoids, lutein, zeaxanthin, and others. And to my great surprise, when I went to scientific meeting, everyone was talking about beta-carotene, no word about lutein, zeaxanthin, or anything else. And anyway, so I will tell you a little bit about the following events. And what I would like to talk about is the distribution of carotenoids in foods and human serum, because that's what's important, and the techniques to separate them and, of course, identify them, because you're looking at not only identifying the nature of the carotenoids involved, but you're also looking at their levels. Techniques have to be accurate. Metabolites of carotenoids in human serum and tissues, and, of course, in human ocular tissues, and then talk a little bit about metabolic pathways of carotenoids, which we proposed in human ocular tissues. We did a supplementation studies with lutein and zeaxanthin in Rhesus macaques that I will talk about, and of course, tell you a little bit about what animal model would be appropriate to use for these kind of studies. Now, here is a picture of fruits and vegetables, and these are, of course, unique in their distribution of carotenoids. Over the years, since 1983, I divided the fruits and vegetables into three categories, basically. The first is the green fruits and vegetables. The next is yellow-orange. And finally, the red fruits that I will talk about. So let's take a look at the carotenoid profile in some of these green vegetables. When I identified a lot of epoxides in green vegetables, and of course, lutein and zeaxanthin, and then I discovered that they, of course, contain lutein, alpha, and beta-carotene. So the first paper I ever wrote on this was basically published in 1986. The reviewer came back and said, this paper is weird. Basically, he said, this author is trying to create creating a tempest in a teapot. And my failing English, I didn't understand what it said. Now, some of you may. I don't even know if this is American slang or British slang. But at any event, I was told that it means that you're trying to stir up the scientific community. And I said, yeah, that sounds good. You know? Anyway, so after that, gradually, it was actually the human eye that focused the attention of scientists to lutein and zeaxanthin. Ironically, it took years for us to come along and look at these things. And then in yellow-orange, the profile is a little bit more interesting because most of these carotenoids are absorbed. Lutein, alpha-cryptoxanthin, alpha-carotene, and there are some structural variation, of course. I always talk about the fact that if, for example, zeaxanthin and beta-carotene got married, their children look like beta-cryptoxanthin. This is the way I teach people that really have difficulties with chemical structures. But at any event, you can see that structural differences. If you ask me, I say all of these carotenoids are very important in our diet, and some of these will actually be very important also for the eye, especially alpha and beta-cryptoxanthin because of the presence of the hydroxyl group in them, and the fact that may not be as easily transported to the macula as you would like them to. We've been talking a lot about carotenoid esters. For the life of me as an organic chemist, I don't understand why we have to saponify at 45 degrees overnight. I never do something like this. You can saponify the worst sample, probably human milk, breast milk, at room temperature in alcoholic potassium hydroxide or sodium hydroxide under nitrogen, and you don't need 45 degrees. Under those conditions, you're not going to convert lutein to mesozeaxanthin. Absolutely not. But at any event, most of the yellow-orange ones contains carotenoid fatty acid esters that they have to be saponified, I agree, and then, of course, analyzed. And we also know that these epoxides are not absorbed into the human blood, and only the ones that have no epoxide ring would be absorbed. And then, of course, this is not probably interesting to you, but I have to talk about all carotenoids. These are the ones that are found in red fruits and vegetables, and they're mostly lycopene, phytofluorine, phytoene, gamma-carotene. Among these is the only one with vitamin A activity that I have labeled it here. So after doing exhaustive analysis of fruits and vegetables and looking at their distribution, and then I basically looked at the human plasma and serum, and what we find is the following. This is how these carotenoids are metabolized. A bunch of these carotenoids that are vitamin A active that are shown on the top, not only they are absorbed intact, but they're also converted to vitamin A. The next group are not vitamin A active, and they are directly converted to, are absorbed. Lycopene is oxidized and directly absorbed to two metabolites which we've identified. And of course, lutein and zeaxanthin, lactoxanthin is a very minor carotenoids in romaine lettuce. But nonetheless, these are collectively oxidized to as many as perhaps 6 metabolites. Carotenoid fatty acid esters are not detected in human plasma. We've looked at them. In fact, I have developed a methodology that you can actually look at the carotenoid esters without saponification as well. This was published probably 25 years ago. And, but these are, in the presence of pancreatic secretions, are hydrolyzed, and then their parent carotenoids are then absorbed. And epoxides, of course, are not absorbed. So we're talking a lot about methodology, and my job as a chemist is to look at these things very carefully. And when I started working on this project, I was looking at, this is for some of you who are ophthalmologists and you have no clue what HPLC is. HPLC is a technique we use for separating various components in a mixture. Each of these peaks are representative of a compound in, for example, in this sample is an extract from human plasma. So therefore, you can actually separate out a lot of these carotenoids by commonly used reverse phase HPLC. And of course, the technique that I developed back in 1984 takes 40 minutes for a single analysis, and this is not very appealing to people that are doing 2,000 samples in a clinical trial. But nonetheless, this is the way it should be done, and I hope that one day people will start doing a little bit more detailed analysis. So let's go through this. Here you got lutein and zeaxanthin combined, a whole bunch of stuff coming out here, which is really not a good separation. It's awful. However, reverse phase is good enough to separate some of these other carotenoids that perhaps you don't care for. But nonetheless, they're there. Alpha, beta-cryptoxanthin, tocopherols, some of the dehydration products of lutein, and of course, we go to zeta-carotene, alpha-beta-carotene, phytofluorine, and phytoene. So let's not worry about this because, after all, you're all here for lutein and zeaxanthin. So what we do then, we take the same extract, inject it on a different HPLC system using a normal phase separation, and what happens here is very interesting. Those compounds that we separated earlier, they bunch up together and come out very early. Awful separation at the beginning, but the section on lutein and zeaxanthin and its metabolites are very well resolved. And that's how we actually identify lutein, epilutein, zeaxanthin, and all these other things. However, there is one more catch. This system does not separate mesozeaxanthin from zeaxanthin, the naturally occurring zeaxanthin. So then we use another separation technique for that. But that just to give you some idea about what technique we use for separation and characterization of these compounds. The other issue is that you have to ensure when you see an HPLC peak, is this really what it is? So you have to actually not only synthesize the compound, isolate the compounds, do full characterization. So I'm one of those people that when I see an HPLC trace without detailed analysis, I'm talking about structural elucidation, I'm kind of worried about this. So you know, you can argue that I'm on the tough side of this, but I think we have to be. We have to be very vigilant about the fact that when you see a peak, is it really what it is? And what technique was used? And how was it separated? Was it actually isolated and fully characterized? So then we found out these metabolites that are present in the human blood. But one of the interesting things is epilutein, which is the epimer of lutein with the hydroxyl group facing up. And then there are oxidation products, so direct oxidation product of lutein. And of course, another carotenoids that we don't see this very much, and a diketocarotenoid. So it appeared to me that in human plasma, the integrity of the poly-N chain system, this is the central part of the molecule, remains intact. But it is the terminal N groups that are modified and give us this metabolite. So now, based on this observation, I made a proposal that this is long time ago, actually, that here's what happens in the human blood, or somewhere in the human body. We don't really know where, but this lutein is oxidized to a compound which I call ketolutein or oxolutein, and this could be reduced then stereospecifically to epilutein because epilutein is absent in our diet. We don't see it in fruits and vegetables. And that's another thing that you have to be very careful. Separation of lutein, zeaxanthin and epilutein and mesozeaxanthin is a job that has to be done with great care. It's not something that you can just inject it onto the HPLC, oh, I see these peaks. These are separated on a normal phase, but the mesozeaxanthin requires a chiral column. So it is possible that there is some isomerization going on here between dietary zeaxanthin and epilutein. We're not sure of this. But one thing that is pretty clear by now, most people agree that there is a double bond isomerization to give us mesozeaxanthin. Now, formation of the other metabolites, I propose that perhaps once the monoketocarotenoids are formed, then there is perhaps further double bond isomerization and oxidation to give us these other carotenoids, which we have actually identified full characterization in the human plasma, all three stereoisomers of diketocarotenoids. So these are, of course, proposals based on what we have identified in human plasma. Now, does this really happen in the eye, or it's actually some of these metabolites are simply transported through the circulatory system into the human eye? That's something that needs to be addressed, of course. To some extent, we can hypothesize things, but unequivocally, I don't think so. Now, obviously, the history of this is very clear. The great contribution by Bone and Landrum that identified the lutein, mesozeaxanthin, and dietary zeaxanthin in the human ocular tissues. What we've done over the years in collaboration with a number of colleagues, Paul Bernstein and Donna Garland at the National Eye Institute, we identified other carotenoids, of course, as well as the oxidation products of these compounds. Now, here is what I would draw your attention to. This is another HPLC system of the extract from human RPE choroid on a nitrile bonded column, which is actually a normal phase. It's not what most people use. And you can see a very nice separation between lutein, dietary zeaxanthin, which, if there was any mesozeaxanthin, would be right here. They're not separated. And epilutein, as well as some of the stereoisomers. These are geometrical isomers when the molecule bends itself, as well as the ketocarotenoids, that oxolutein, which is right here, to a lesser extent. Now, you have this separation. You have no clue how much mesozeaxanthin is in there. And you want to find out what technique do I use to separate all of these, right? You need to go to a chiral column. This is actually not any natural product sample. This is actually standards that I synthesize in my lab. And I put them all together and inject them on a chiral column. And you can see the chiral column gives us the ability of separating SS-zeaxanthin, another one that we haven't been talking very much about, the mesozeaxanthin, and dietary zeaxanthin, lutein, and epilutein, and these are a bunch of geometrical isomer, as well as lycopene, which is actually present in many of the ocular tissue, with the exception of the macula that we're going to talk about later. So this is the technique that actually unequivocally shows us if there is mesozeaxanthin or epilutein or misidentification can be avoided. Now, let's take a look at another profile. This is an extract from the human plasma, panel A. And in the panel B, we have
the RPE choroid. Both of these are actually done on a chiral column that allows us to see mesozeaxanthin. Now, when you look over here, of course, don't worry about lycopene and all that, but you can see the zeaxanthin and lutein and epilutein. And this one, of course, is panel A is human plasma. There is no mesozeaxanthin in human plasma. Now, let me finish this, and I want to make a comment about what we've heard so far. And then, of course, when you look at the human RPE choroid, you can see the presence of the mesozeaxanthin, zeaxanthin, no SS zeaxanthin, because if there was any, it would show up here, and of course the lutein and epilutein. Now, we hear a lot about mesozeaxanthin possibility of existence in foods, and what I will tell you is that, okay, maybe integument of fish, definitely integument of fish contains mesozeaxanthin. How many of you eat the fish with the skin, right? So you'd be, the amount of fish, dietary fish that we intake from usual dietary intake doesn't have that much skin in it, or even if it did, it would be very limited amount. But in human blood, over and over and over, we look at there is no mesozeaxanthin. So let's say there is mesozeaxanthin everywhere in the diet. The bottom line is it doesn't exist in the blood. It's not in the blood, okay? And let's move on further. Here is a chiral column that shows the human liver, where all the action is taking place, right? This is where everybody goes to see things happening. Now, when you look at the distribution of carotenoids in the human liver, don't worry about lycopene right now, zeaxanthin, lutein, and there is no mesozeaxanthin, okay? So human liver doesn't have it. Now, of course, there's a counter argument to all this, is that how many human liver did you look at? 2,000? No, we didn't. This is a limited number of samples, so it definitely is subject to critique. Then we're going to look at the human macula. The human macula is pretty interesting. We're all here for that. And then here is the SS zeaxanthin, only present in about, well, not only, 8%, significant. 23% mesozeaxanthin, 69% zeaxanthin, and of course this is total of zeaxanthin, not lutein included. But so you can see that the human macula contains SS zeaxanthin, meso, and of course zeaxanthin. And then we are always, with the help of my colleague Paul Bernstein, we've been very interested in a human ciliary body. This is a tissue that actually is right here, and it's important because it could be the source of a disease called presbyopia. And we, of course, we find a wide range of carotenoids and their metabolites in the human ciliary tissues, which I don't see much interest here in this conference, but I think when we look at ocular tissue, we've got to look at everything, right? So, but in any event, in the human ciliary body, you can see that there is mesozeaxanthin, zeaxanthin, and lutein, and to a lesser extent, epilutein. This is, again, chiral separation that allows us to see everything. Here, again, once again, the structure of the metabolites of carotenoids, which I'm going to move away from. I want to tell you about a study we did with Rhesus macaques, and this involved a number of monkeys that, not my colleagues, of course. These are people who were, I didn't work on them. They were helping me. But in any event, these people really, you know, one of the greatest thing, a speaker came to our university and he said, what do you think makes a great physician? And good school, Harvard, Yale, what? And of course, those things are important, but he said, the person who knows his limitation, right? So I knew my limitations, so I went and recruited all these people, and we actually conducted a very nice study with monkeys. And the research question was, how does the long-term supplementation with megadoses, not your usual intake, will actually result in accumulation of lutein and zeaxanthin. We looked at both of them and their combination, and of course to see if we can figure out anything about the metabolic pathways of these carotenoids. And of course we wanted to know the toxicity or side effects of these supplemental carotenoids. And these, I'm not going to go through all of these details. Unfortunately, I don't have that much time. But I just want to let you know that these are the things that the study parameters. We gave them 10 milligram per kilogram body weight of lutein. This is 60-fold that of lutein in the study that we did with Dr. Emily Chu at the National Eye Institute, where we gave 5 and 10 milligram per day. And then it corresponds to about 150 to 300 times the average dietary intake of lutein and zeaxanthin in the United States. So this is really, really pharmaceutical dose, perhaps, or mega dose, whatever you want to call it. So this is the study design. We had a bunch of monkeys that we had only 3, because of lack of funding, only 3 control animals. Then we had 5 in the lutein group, which I refer to as L-treated group for lutein. And we actually took samples at various points. Eventually, they were sacrificed. After 12 months of supplementation, we let some live, and the other ones were sacrificed. And then we look at the levels of carotenoids in the ocular tissues as well as blood. So these are the L-treated group. And when we gave lutein in these, to these monkeys, then you see a significant increase in the amount of lutein in the plasma of these monkeys. And this is not surprising, no earth-shaking results, really. But it just tells you that you give lutein, you're going to see lutein increasing in the blood, right? So not going to make big deal out of this. But what is important to me is that if you give lutein and lutein intake increases, the oxidation product, direct oxidation product over here, it would also correlate it with the increase in the lutein concentration, which tells us a little bit about the fact that it's not unequivocal. We're going to do labeling studies to prove this, but that the oxidation of lutein takes place, again, perhaps in the blood, somewhere in the human, in the monkey's system, but perhaps also in vivo in the eye. And that's really the bigger question of all. Is it coming from blood, or it's actually already it's taking a different pathway in the eye and is oxidizing in the eye? That we don't know, and I don't claim that I know the answer to that. So, and then we saw an increase in the amount of epilutein. That's not surprising, because once lutein is oxidized to ketolutein, look, there is no one-way street in life, right? If all the streets in Cambridge were one way, then they would be in traffic, right, forever. So if lutein is oxidized, there must be a mechanism to either get rid of it, oxidation products, or recover it. And the body is an amazing piece of machinery, and it does that. So perhaps the formation of lutein, ketolutein, mesozeaxanthin, epilutein, all of these are in a network that allows us not to accumulate particularly one carotenoid that is not of natural source. And this is the eye, of course, and I want to show you some increase in the amount of lutein that you can see in the ocular tissue. This is retina. This is neurosensory retina. We didn't look at the macula for many reasons that I don't want to go into. But at any event, you can see a 4-fold increase. And here is the mesozeaxanthin level. Interestingly enough, there was no significant difference between controls and the ones that were fed lutein. But after between months 12 to 18, there is a significant increase. And the levels of oxolutein went up. With regard to ciliary body, only increase in the lutein level was what was noticed. And here's some p-values for you for oxolutein. Okay, I said that already. And supplementation with zeaxanthin was also the same study design. Basically, at months 6 and 12, we took samples, and then for 6 months, some of them were allowed to go on without supplementation and then sacrificed to look at their tissues. And here again, the levels of zeaxanthin went up. And with regard to ketolutein was very interesting. This, to me, is one of the most amazing stuff that is happening. We've been saying that ketolutein is a direct oxidation product of lutein. But here, we give zeaxanthin and the amount of ketolutein goes up. Whether it's happening in the monkey's circulatory system or in the eye, I don't argue that. But I certainly agree, I would like to think that zeaxanthin was somehow able to increase the level of ketolutein. And this, from chemical point of view, has some very interesting implications. And again, we go back to the levels in the retina, neurosensory retina. You can see an increase in the in the lutein zeaxanthin-fed monkeys, significant increase. There was a big variation here, not significant. But mesozeaxanthin, this is another piece of puzzle that really we don't understand, but the only explanation for this is if keto-lutein went up, why mesozeaxanthin went up when we gave zeaxanthin? We've been saying mesozeaxanthin comes from lutein. But now, here is the tempest in a teapot for you, right? Many of you are going to say, no, I don't believe you. That's fine. We will see. We continue our research. You either disapprove it or it will be proven eventually. But that's not the point here. The point is that we are supposed to give our opinions, and if you don't like it, well, this is a free country. And anyway, so mesozeaxanthin levels went up, which suggests perhaps mesozeaxanthin could be something between zeaxanthin, oxolutein, and mesozeaxanthin is in place, is in action. So we'll find out about that. And with regard to ciliary body, what was very interesting is significant increase in the amount of zeaxanthin. So now, almost going to end this, and I'm going to move on very quickly. This is a metabolic pathway that I already told you about, so I'm going to finish up. I just want to tell you a little bit about animal models. Quails, we think, is a good model because it doesn't have a macula. It's another tempest in a teapot, but then we'll move on from that. And here we got zeaxanthin, lutein, and epilutein. It's got all the carotenoids that you want. Here is lutein, mixture of mesozeaxanthin and zeaxanthin. In the liver, 1% mesozeaxanthin, but when you go to the blood, mesozeaxanthin is actually on the chiral column, 1%. So move on into the retina, and you can see very trace amount of SS, 10% of the meso, and this makes it a very good model for us. I'm going to have to skip some of these slides because I feel really rude to take more time of yours. And I'm just going to tell you a little bit about frogs that are a little different because frogs is hard to get blood from. The blood coagulates very fast. So, but frogs have a very interesting system in the sense that they have a lot more SS zeaxanthin. So if you look at some of these values, you can see, and I'll be glad to send the rest of my presentation, or all of my presentation, to any of you that are interested, because I feel bad going through this rather quickly. So let's move on and talk about a little bit about metabolism here. I'm going to finish over here. And in frogs, it looks like zeaxanthin, or for that matter, SS zeaxanthin is formed from this molecule, which is actually pretty unstable in the lab, but somehow in the human enzymatic system may exist. So the question that really needs to be answered is this transformation between zeaxanthin and mesozeaxanthin, or SS zeaxanthin for that matter, and just really complicated stuff. But the only way to do this is labeling studies and feeding animals. And this is some summary with the levels between humans and quails. And with that, I'm just going to conclude that mesozeaxanthin could be coming from anywhere. Let's say that. All right? And quail and frog retina have the right enzyme for doing that. And here are my collaborators and, of course, people who have supported our research. Thank you for your attention. I'm sorry if I went over.
Sorry to hasten your end. It was a very interesting talk. Just a quickie before I throw it open. You say we don't eat skin of fish. What about when we barbecue? What about when we barbecue fish? I mean, very often in Latin countries, they barbecue fish. The skin is eaten. Does it destroy the carotenoids?
Yes, barbecuing probably barbecues the carotenoid. That's what I think. Okay. Because they're heat-sensitive compounds. Of course, if they're in the matrix of the animal tissue, maybe they're preserved. I don't really know. But that's a good question. I don't know the answer to it.
Thanks.
Yes.
Here, Casey.
Oh. May I, in the meantime, ask mine? Because I have the microphone in here. So. I noticed that in the monkey research, if you compare the controls with the 18-month results of the intervention, then consistently this 18 months seems to get lower retinal levels compared to the controls. Can you comment on that?
Oh, that's a good question. I don't really know. Because perhaps when you remember, we gave mega doses of lutein. So sometimes, you could actually increase the levels of lutein by very small amount of supplementation. We did a study with Dr. Emily Chu at the National Institute. We only gave like 5 and 10 milligram and 2.5 milligram of lutein per day for 6 months. And that resulted pretty much in the same increase that we saw in the monkeys that were supplemented with mega doses of these lutein and or zeaxanthin. And so that means that perhaps not everything is become bioavailable. The other issue is that you got only 2 or 3 control animals, and you got 5 over here that are supplemented. Look, this is not a statistician can make up numbers to make it look good, but certainly the fact is that we just didn't have enough monkeys, and the initial proposal to NEI was more 36 monkeys. But of course, to house 1 monkey for 1 year, you can send your kid to college. So that's the problem.
Dr. Bairstein.
Do you want to go first? Just a quick question in response to what Dr. Nolan had presented. Did you look at your lutein to find out if there was actually mesozeaxanthin in it when you were doing the supplementation?
I've been closely working with Chemin. At least I can talk about that one. The supplements of Chemin do not contain any mesozeaxanthin, and I have worked with that extensively for almost more than 20 years. And we've used the same methodology that I described. I do not see any mesozeaxanthin in lutein supplements. But you know, who knows? Other supplements I cannot vouch for.
So do you think then that our finding is due to the manufacturing step? Is there something happening there? Because we definitely see it.
I really doubt it, because look, one of the things is that I, as a chemist, I was very interested to take lutein and convert it to mesozeaxanthin, right? So I use all the possible techniques. The best way you can do this is 70-degree reflux in hexane in some kind of an emulsion system. It was so hard. I was so frustrated. I said, why don't I just take the double bond and move it over like this? You know, it just can't do it. It just doesn't happen. So I doubt it unless you use a very strong basic conditions and heat. You're not going to convert lutein to mesozeaxanthin. So there may be other dietary sources of anything else in the population. But again, the last point of discussion should be human blood. We've looked at perhaps about 400 extracted blood samples, no mesozeaxanthin in the blood and liver. So not 400 livers, but.
Yeah, I mean, I'd love to send you some of the blood samples we have, maybe, that you could look at them on your methods, because it's clear.
Dr. Howard for funding?
Yeah, no, but they're supplemented, yeah.
Okay.
Sure.
Another question.
One last question.
Yeah.
I'm always interested in the xanthophyll epoxides that you never see. We eat a lot of them. You never see it in the blood or anywhere else. Do we know, are they truly not absorbed and just passing through, or are they being metabolized, or what's going on? Do we know?
There are no epoxides, I can tell you, in the human blood. We've looked at them so carefully. There is no epoxide in human blood. And there are evidence that the humans do not like epoxides. I mean, if you look at literature with regard to some of the natural products, I mean, epoxides are excreted. We have found it in feces. But that doesn't mean that
so
somehow they're not modified in the stomach,
yeah.
but or anywhere else. We don't see them. We don't see them in the liver. We don't see them in the plasma. But if they are somewhere else, and we have looked at human tissues, all tissues, but we don't find them.
I think we've got to stop there. And any further questions? Thank you very much indeed.
Sure.